Okay, so you all have the notes, so I can just start exactly where I left off yesterday. Who's this? So this was the Siegel upper half space. D by D complex matrices that are symmetric and have positive definite imaginary part. And I was explaining that this is parameterizing isomorphism triples, the isomorphisms, classes of triples like that, where A lambda is okay. So PPAV, principally polarized abelian variety. Over C of dimension D. And then the eta is kind of, well, infinite level structure in a way, but so it's an isomorphism between H1 of A and Z to the 2D that is symplectic isomorphism. So if you remember, this has a symplectic form coming from a polarization, and this I just put the standard, well, the standard like 0 identity minus identity 0 symplectic form on it, which I mean, it doesn't really matter. I just need to fix one. Perfect symplectic pairing, and this map, I mean, if I call it iota, it just sends X to the abelian variety C to the D modulo the lattice Z to the D plus X Z to the D. So that's lambda X. And then this polarization is given by this. So there was a question about that. So this so we saw that polarizations correspond to Hermitian forms on the D algebra, which here I'm just taking to be C to the D. So this is the Hermitian. I'm taking the Hermitian form that has this matrix in the standard basis of C to the D. Okay, and I know that this matrix is definite positive. It's symmetric definite positive. So, and then the obvious isomorphism. So lambda X to Z to the D that I wrote, Z to the 2D that I wrote last time. Okay, great. So now let's talk about level structures. So, so remember, I'm trying to, what I'm trying to understand really is quotients of that by arithmetic subgroups of SP 2D of Z. So here, for example, I could say, so, I mean, on here I have this symplectic group acting. For example, if I just want to understand the quotient of that by SP2D of Z itself, well, how does SP2D, okay, so I don't, maybe, oh, here. So there's SP2D of R, so at least I can tell you how SP2D of Z acts on this part, it acts on the eta. You know, you compose the eta by an element of SP2D of Z. So what does it mean taking the quotient of that by SP2D of Z? It just means that I forget this. So I'll just get isomorphism classes of principally polarized abelian varieties of dimension D over C. However, I don't just want the quotient of that by SP2D of Z. I want the quotient of that by maybe congruent subgroups of SP2D of Z, or things like that. So that means I don't want to forget all of the eta, but maybe I just want to remember a small part of it. So the answer is going to be that, okay, the thing I will remember is called the level structure on A lambda. So let's define that. So take n a positive integer and take A lambda, principally polarized abelian variety, and well, okay, I'm going to write PPAV even if I'm over another basis. So over some scheme S of relative dimension D, And so a level L structure, a level N, sorry, structure on A lambda is a pair eta phi where, well, eta, so if you've seen elliptic curves, this should look familiar. If you've seen level structures on elliptic curves, so eta is an isomorphism between the group of n torsion points on A and this constant group scheme here. And I don't just want it to be an isomorphism. I mean, it's called eta, just like the eta here, so I want it to be a symplectic isomorphism in some way. But for this to make sense, I mean, oh, here I have the veil pairing. It lands in mu n. So the veil pairing defined by lambda, here I will have eta. Here I have this, z, both. Here I have the symplectic pairing that I've been using. Here that lands in z over nz. So if I want to compare the two, I did an isomorphism between these two group schemes. So that is the second part of the level structure, the phi. Okay, so I can also think of phi, I mean, or I can also think of phi as a primitive section of this scheme. Mu n is the scheme of nth root of 1. Of course, that's the same. So, of course, a level n structure is only going to exist if there exists such an isomorphism so that forces n to be invertible on S. It's actually equivalent. And then you need this scheme to be constant. Okay. So now, right. So corollary of this is that if I look at this gamma n, which is the principal congruous subgroup of matrices in sp2n of z that are equal to the identity modulo n, then this map iota is going to induce a bijection here with the isomorphism classes of triples like that, where A lambda is, well, is as before. So maybe, you know, principally polarized abelian variety of dimension d, and eta is an isomorphism like that, such that eta e to the minus 2i pi over n is a level structure. Okay, and why? Okay, why is that? I mean, if you look at this, maybe I can explain a little bit. So if A is this c to the d over lambda x, like over there, then what is an? So 1 over n lambda x over lambda x. Okay, and so I have an isomorphism. I mean, the eta z I have over there. And this has a natural isomorphism with z over nz to the 2d. And if I want this to be a symplectic isomorphism for the Vel pairing corresponding to lambda, well, I have an explicit formula for that Vel pairing, and it involves e to the 2 pi I n h of xy, where h was the the Hermitian form that I'm using. So that's why I have to use this e to the 2 minus 2 pi I n. Oh, sorry, it was e to the minus 2 pi I n h of xy. So I'm pretty sure that's the correct primitive nth root of 1. And if it's not that, it is inverse. Did I mention all the signs are wrong?
No, 50% chance.
At least 50%, because I'm doing worse than chance. Anyway, so the map, right, so the quotient map, here I'm giving you the quotient map from HD plus to that quotient here. So if you have a lambda eta, then a lambda eta z like this, then the eta z is going to induce, so this is like eta z. Eta z is going to induce a level structure, a level n structure for that particular primitive nth root. And then I'm telling you that that gives you the bijection. Okay, and okay, I guess the reason this works is strong approximation. That map is surjective, so you need to use that somewhere. Okay, anyway, what is the point? I mean, this is all nice and all. Well, the point of that is that this now, these triples A lambda eta, I have looked at them over C, but I can look at them over other base schemes. So they're going to define a moduli problem whose C points are this quotient. Then maybe if I'm very lucky, that moduli problem is representable, and I'll get a model of that quotient over a number field. Okay, well, let's do that. So what do I need? So to make sense of that moduli problem, I need a primitive nth root of 1. So I'm just going to give myself. So I'm going to invert n. Okay, that was very stupid. I'm going to invert n because I want isomorphisms like that to exist, and then I'm going to give myself a primitive nth root of 1. Which I'm going to call zeta n. So zeta n here is the class of T, and so this embeds into C by just sending zeta n to this e to the minus 2 pi I over n, and then definition m prime dn. So that's a functor from schemes over On to sets, and it sends a scheme S to, well, isomorphism classes of triples like this, where A lambda is a principally polarized abelian scheme over S of dimension Z, and eta zeta n is a level structure. Let's see. What? 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 Why is this so short? There was a longer one yesterday. Oh, okay. I was going to steal Yanis's project. Okay. So this is a nice functor, and I define it so that the C points, well, are still there, bam, isomorphic to this. And then the theorem, which I'm totally not going to prove, of Mumford is that if n is at least 3, then m prime dn is representable by a smooth quasi-projective scheme. So over On of relative dimension d plus 1 over 2. And I'm pretty sure connected geometric fibers. Certainly the geometric fiber, the geometric generic fiber is connected, but I think they're all connected, but don't quote me on that. Okay, so that's great because, I mean, in particular, what do we get? Well, this nice locally symmetric space, which we already knew was an algebraic variety over C, actually has a very natural model, and a very nice one, over, so if I want it over a number field, I get it over Q e to the minus 2 pi I over n, and even over this ring of integers On, okay. Well, not quite the ring of integers because I inverted n, but we'll come back to that. Okay, so that's very nice, except for one small, okay, there's the fact that I took gamma n and not gamma, but like the gamma n's are cofinal in all arithmetic subgroups, so that's, maybe I'll talk about that more when we are adelic, but that's already, I mean, you could cook up models for the other gammas from that. The bigger problem is that the field over which the model is defined depends on n. So it depends on the level, and that's kind of annoying because we wanted all the Hecke correspondences to descend to the models, but the Hecke correspondences are between different levels, so it's not really going to work out in the best possible way. So we want a bit, I mean, we want to go a bit further. Of course, the integral model is also dependent on something that depends on the level, and here we're going to be stuck with that. But for canonical models, we can do better. Okay, so how can we do better than that? I mean, better, I think if Milner was here, he would tell me that's not better, maybe. I think he likes connected Shimura varieties, but... So here we did something a little bit unnatural in the level structure. I fixed the second component to be a particular primitive nth root of 1. I don't know if you can see it over there. Here it is. Okay, so what I could do if I want a moduli problem that's defined over Z is to let the second component vary too. Okay, so this is the actual modular problem that I care about, so that's why it doesn't have a prime. And okay, I'm going to define it. So I can't really get around this inverting n if I want level structure to exist. But so I'm going to define it over Z1 over n. I mean, it makes sense as a moduli problem over Z, but it's just it would have empty fibers outside of this open subset. And you just send S to the isomorphism classes of A lambda, eta phi. A lambda is as before, and this is a level n structure on A lambda. Oh, sorry, I realized I forgot to say something about this theorem. Well, one thing I can here. So the theorem of Mumford. I actually also works, except this one doesn't have connected geometric fibers. Yeah, I forgot to say, why do I need to take n greater than or equal to 3? It's because I defined the moduli problem in a somewhat unnatural way. I took isomorphism classes here. Of course, the more natural way is to see it as a functor with values in groupoids, and to just send S to the groupoid of these things, where morphisms are isomorphisms. What happens if n is at least 3? It's a theorem of Serre that these things don't have non-trivial automorphisms. So then it doesn't really matter. Your groupoids are all actually equivalent to sets. So if n is 1 or 2, this theorem still works, but you just have to use, you just have to use the correct moduli problem, and you just have to say the Lim-Mumford stack instead of scheme. Which, for the kind of problems we worry about, we can always take the level to be a little bit deeper. So this is kind of a detail for us. Okay. So anyway, so if I change the moduli problem to be this one, then now I get a very nice scheme over Z1 over n. So now I get a model of something over Q. So the question is, what do I get a model of over Q? So what are the C points of that guy? Well, okay, I'm again kind of confused by the order of the boards. Yeah, I can erase that. Well, it's not very hard. What happens over C is that I just allow the primitive nth root of unity to be whatever I want. So I'm just going to get a disjoint union of copies of what I had before, indexed by the set of primitive nth roots of unity, basically. So I'm just going to repackage it in a slightly friendlier way, so it looks like a Shimura variety. Let me introduce for this the general symplectic group. So the general symplectic group is just symplectic automorphisms of the same form as before, except now I only require the automorphism. So I don't require the the G to fix the symplectic form. I just wanted to fix it up to a scalar. Okay, where this C of G is in GL1. So here I'm giving you the recipe for R points for every commutative ring R, GSP2D of R, the set of G in GL2D of R, such that this, where C of G is an invertible element of R. So this has it comes with a character into GL1, and our symplectic group is just the kernel of this. And this guy, so if D equals 1, the symplectic group was SL2, and this is GL2. And C is the determinant. So this, it does not act on HD+, but it acts, so GL2 of R does not act on the Poincaré upper half plane, it acts on C minus R. So let's introduce the analog of C minus R. So D by D complex matrices that are symmetric. Okay. And whose imaginary part is either positive definite or negative definite. And this one has an action of GSP2D of R. And the formula is exactly the same as for the action of SP2D on HD+. So it's like ABCDX is AX plus B times CX plus D minus 1. Okay, and this action, again, you can prove it's transitive. And the stabilizer in GSP to D of R of the base point we used is, so it's the, well, the general orthogonal group intersected with GSP2D of R. And it's actually just scalar matrices times the stabilizer we had in SP2D. So this one is going to be a symmetric space for the general symplectic group. And this, okay. Whoa, okay. Ah. What? Where is it? Oh, here you are. Okay, I felt like this is an intelligence test and I'm like failing it. You have to do the task in a certain order. Otherwise, you don't get the reward. Okay. So the, I guess, corollary, maybe I'll make it a new proposition. What are the C points of this? They are just in bijection with this GSP2D of Q okay, adelic double quotients are so messy. So with this adelic double quotient, where Kn is just the adelic equivalent of gamma n, so it's the group of matrices in GSP2D of Z hat that are trivial modulo n. Here, okay, so this is, this is what I was calling MKN last time. Of course, M should be MKN for GSP2D. Okay. Then how do you prove that it's this one? And one way to do that is you basically, so you eat the sign. So this is the ones that have a C greater than 0. And then this doesn't move. And then this, so this thing is connected, and then the connected components of this are indexed by this double quotient, which is a finite set, and this, by strong approximation, is going to be actually isomorphic to this thing here. I mean, particularly the image of everything by C, and this is just, well, Z hat cross over 1 plus N Z hat. And this is just, damn it, this is isomorphic to Z over N Z cross. And then you just, so each connected component, I mean, we saw that last time, each connected component is going to be HD plus divided by some gamma, and then you just check that you get the correct, you basically just get gamma n every time. Okay, so what is the lesson here? I mean, why do I annoy you with that? Is that now, so now this is defined over Q, which you will notice does not depend on N. well, actually it's defined over Z1 over N. But so this adelic locally symmetric varieties for GSP have models that are all defined over the same number field regardless of the level. So this is a kind of a general phenomenon. So the adelic double quotients with reductive groups have better, well, rationality properties than these connected locally symmetric varieties that we started with. So if you want to have a clean theory where all the whole tower of Shimura varieties with varying level is defined over one number field, then it's better to go with adelic double quotients. Okay, let's see. A second lesson that I guess I'll have to come back to is that here we don't just get models over a number field, we actually get integral models. So over this Z1 over N. And integral models, you can't really hope that they will all be defined over the same ring. So unfortunately, well, what happens is that the varieties are going to have bad reduction at certain primes that depend on the level. So the smooth integral models will be defined over a ring that depends on the level. Please don't ask me what bad reduction means for a non-projective variety. It's a heuristic. I mean, anyway. Well, I guess I mean the toroidal compactifications have bad reduction. So with all that kind of motivation, let's define Shimura data. This definition due to the Lyon. Although the Lyon would tell you it's due to Shimura. So the Lyon has a Bourbaki paper that's called Travaux de Shimura, where he just like lays the foundations of Shimura varieties, and it's based on Shimura's work. The Shimura was working with this X over gamma, disconnected locally symmetric varieties, and what the Lyon did is like basically maybe this thing that I was trying to explain, like how do you group them together to get something that has a chance to be defined over a number field independent of the level. One of the things he did in that paper. Like give a point of view that will produce varieties defined over one number field. So Shimura datum is a pair GH, where G is my connected reductive group over Q. And H is from a map from a C cross to G of R. So it's a morphism of R algebraic groups. So here I don't have time. I can't spend as much time as I should on this very interesting algebraic group over R. This is, of course, the value reduction of scalars from C to R of GL1. And it's a group that its representations basically classify pure Hodge structures. Yeah, so quite interesting. And so what do we want? So we want H of R cross to be central. So H, if you remember, there was that morphism U from last time. And I have to say something because I actually made a mistake last time when I talked about U. But there was that morphism that would tell you when a group had a Hermitian symmetric domain as a symmetric space. And U is basically H up to factor 2. So the condition is here, the characters of C star on the Lie algebra of G. So let's say GC. So C star acting by add times H. They're all among 1, Z, Z bar minus 1, and Z minus 1, Z bar. Okay, so this, as an algebraic group, its characters are Z and Z bar. Okay, this is again, this is an algebraic group over R. I'm kind of insisting because I was very confused when I first saw that. And the third part is conjugation by H of I is a Cartan involution. On G there, the derived group, the R points of the derived group. So this U, the conditions, there was very similar conditions on U, except I think I kind of messed up. I said conjugation by U of I is a Cartan involution. It should have been U of minus 1, because the way U and H are related is like this. So let me give you an example. Well, let me give you the example, because this is the only one we've had so far. So yesterday I told you that was U. That's not true. U of A plus IB is H of a square root of A plus IB. So that is only well defined in the adjoint group. Why? I mean, it's well defined in the adjoint group because H of minus 1 is central. So if you actually try to work through my example, U is supposed to have characters 1, Z, and Z minus 1 on the algebra, and the U I gave yesterday had characters 1, Z squared, and Z minus 2. Because okay. Anyway, so the notes on my own website are already corrected. There is a link. If you go to the Dropbox, at the beginning of the notes, there is a link to get the latest version. And the latest version has been corrected. Okay, there are various conditions that you can add. The most popular one being that G add doesn't have any anisotropic. G add doesn't have any factors that are anisotropic over R. So I'm not at that level of detail, so I'll ignore it. This is Lyon's original definition in that paper, Travaux de Shimura. And once you have that, then for every K included in, well, yeah, okay. Then, of course, I forgot to define something, but that's okay, I will do it now. Then you introduce X, which is G of R divided by the centralizer of H. And then the associated Shimura variety is this. So the associated Shimura variety at level K is defined to be this. So this is Shimura variety at level K. Okay, so X is also, you can also think of it as the GR conjugates class of H, of course. And this guy here is a complex algebraic variety. It's quasi-projective. And why is that? Well, okay, so it's like some calculation I did last time. This one is just a finite union of some gamma I under X, where these gamma I are just the intersection of G of Q with some conjugates of K. Okay, X might not be connected. For example, in the case of GSP, okay, so I'm saying this is an example of a Shimura datum. In the case of GSP, H is going to be this HD that we still have on the board. It's not connected, but that's okay. It has connected components. All the connected components are like symmetric spaces for groups related to G, like maybe the adjoint group of G or something like that. The H will cook you up a U that satisfies the conditions of last time. And so basically these are all finite disjoint unions of Hermitian symmetric domains. And so we can apply the results from last time. So finite union of Hermitian symmetric domains. Okay. And now the real meat of the Lyon's paper is defining what a model of that is. What should the number field be, and what conditions should the model satisfy? Oh, okay. Well, this is ridiculous. I think I've even slowed down compared to yesterday. Okay, so let me just quickly define morphisms. So a morphism of Shimura data, so G1, H1 to G2, H2, what is it? Is a morphism of algebraic groups, U from G1 to G2, such that U from G1 to G2, so U composed with H1 is conjugate to H2 under G2 of R. And once I have that, well, it gives me morphisms between the Shimura varieties. Under the condition that you can guess on K1 and K2, I mean, K2 has to contain U of K1. And then you have an obviously defined morphism here. So, okay, canonical models. So first I'm going to give you the recipe for the field over which the models are going to be defined, and then I'm going to justify the recipe. I guess maybe there's a proposition of the Lyon, which is kind of useful. It says that if U is injective, you can always choose, for every K1, you can choose K2 to make this map into a closed embedding. It's useful, but I'm not going to prove it, so. Okay, so so we have this map from H from C cross into G of R. And so C cross is the R points of this torus S. which is sometimes called the Serre torus. And so H induces a map from S of C into G of C. Okay, but S of C is for an exercise, it's actually C times cross C times. Okay, so we're going to look at the first factor. And here I didn't tell you what the two factors are, so this is totally meaningless. So this one is Z and this one is Z bar, okay? So I'm looking at the factor Z. Do the exercise yourself to calculate S of C, it's fun. So I look at this, bam, and I'm going to call this composite character mu H. Okay, so mu H is it's a co-character of G that is defined over C. And the reference field which I like to call F, although a lot of people like to call it E. Actually, I should call it E. So the reference field is the field of definition. So it's a subfield of C. It's naturally a subfield of C. It's the field of definition. Well, I want to say the field of definition of mu H, but that doesn't really make sense because H is only really relevant up to conjugacy. So I'm going to say the field of definition of the conjugacy class of mu H. Okay, cool. So exercise solution in the notes. In this case, well, first exercise, calculate mu H. Not very hard in that case. Second exercise, calculate the reference field, find that it's Q. Okay, more fun exercise. Didn't have time to introduce the unitary Shimura data.
Sophie, what kind of co-character is this?
It's a minuscule co-character. That's why it's called mu. Thank you. Yeah, should have said it maybe. Okay. As you can see, the condition on H is that the characters of H on the Lie algebra are 1, z bar minus 1, and z minus 1 z bar. So if I make a GL1 act on the Lie algebra for mu H, what characters am I going to get? I'm going to get 1 z minus 1. Okay, so let's do another example, kind of a trivial example, the example of tori. So if G equals T is a torus, then actually for any H, TH is a Shimura datum. Okay, I mean, if you look at the conditions on H, which I erased, but that's if G is a torus, they're all trivially true. Great. What is the Shimura variety? But what is X? X is the conjugacy class of H, so X is a singleton, because G is commutative. The Shimura variety. So what do I get? I get T of Q over T of A, F over K. So that is a finite set. So I have a finite set, and I say, well, it's an algebraic variety over C. I mean, yeah, that's my right. certainly. And I want to define it over some subfield of C. Did I tell you that F is automatically a number field? I'm telling you that F is automatically a finite extension of Q. Yeah. So I want to define this over F. So what do I need? I need an action of the absolute Gala group of F on this finite set. Okay, so I just need to give you a recipe to define an action of the absolute Gala group of F. What is the E? Yes, E. What is the reflex field? I mean, in that case, E is just the field of definition of mu H.
So there's F and Q there, so I guess.
Yeah, there should all be E's. Yeah. Was there F?
No.
Yeah. Okay. So it's the field of definition because my conjugacy is trivial. Great. So what can we do? So we can start from GL1 over E, and here we have mu H goes into T over E, and then here I can apply the norm to land back into T. I guess, well, okay, technically if I want to be very, very rigorous, I want all of this to be algebraic groups over Q, so I put veiled restrictions of scalars here. So this I'm going to call R, the reciprocity map. Okay, and now what is the recipe? Well, R is going to give a map from pi 0 of A cross over E cross to pi 0 of TQ under TA. And this being a finite set, this actually subjects on this Shimura variety at level K. Okay, and this by global class field theory is isomorphic to the abelianization of the absolute Gala group of E. Right? Did I say something wrong? Okay, so here somebody asked me, how do you normalize global class field theory? And I say, well, okay. So apparently Lyon's normalization is uniformizers go to geometric Frobenius. So this is how I normalize it. Okay, so, well, this defines an action of this on this. Yes, this is a morphism of groups. So hence a model okay, and now again, if somebody read Lyon, you're going to say, but Sophie, in Lyon he takes R-1. And I'll say yes. However, in Lyon, he also takes HD-1 here. And for various reasons, I don't want to use HD-1 because HD is very nice. It actually extends to a morphism of algebras here. So because of that, and because I want the MDN to be the canonical model, I changed the sign of the reciprocity law in Lyon's paper. And by doing that, I probably broke 12 other things. But I guess let that be a lesson to you. Don't mess with science. Oh, sorry. Okay, so now back to the general case. So you have this Shimura datum GH. So what is a canonical model? So a canonical model of, so the Shimura, so I said, we're not going to just descend one Shimura variety, we want to descend the whole projective system of Shimura varieties. So what is that? It's a model, or like, well, it's a projective system MK GH of varieties over E with what the Lyon calls a smooth action of GAF. So, okay, basically it means like Hecke correspondences between these things satisfying all the conditions you would expect. So see the notes for a precise statement. It should be a model, so with an isomorphism of this with the ones over C. Okay, so I want an isomorphism that is equivalent. Okay, and okay, so that is all like a model, a reasonable model, and with the following condition, such that for every injecting morphism from a torus into G, all the morphisms. So this is going to give a morphism of Shimura data from T with this H times U into GH. So I'm going to get morphisms of Shimura varieties like this. I mean, if I choose the levels in a reasonable way, and these morphisms should all are all defined over, wait, so maybe I want, oh, yeah. They're all defined of the reflex field of this Shimura data, but this one contains the reflex field of GH. Because if the
C points, if your morphism, you took the C points, you may not taking the C points. Defined.
So so I took the C point. So this is a morphism because so this morphism that I know how to define on C points, I'm saying that it descends to the models. So that's the condition.
Sorry?
Yes.
Sorry.
Oh no, not you.
You want just the general morphism of Shimura data? Well, I don't think H composed with U makes sense.
Wait. Oh, you're right. You're right. So I'm just going to put H prime here. So maybe let's put it like this. Thanks. But well, okay, I said it should be injective on the algebraic group part, but even that's not very important. I don't think so. Well, I mean, for this maybe, yeah. So, right. So what can I say in like 2 minutes? And then, well, of course, when I say they are defined over this, I just means that for T, I just take the model that I just defined on this board. So why is that reasonable at all? Because those, so in general, the image of an injective morphism between, I mean, if I have an injective morphism between Shimura data, it defines closed immersions between Shimura varieties. The images of that are called special subvarieties. Here, the case where this is a torus, so this is just a finite set, the images are called special points. So what the Lyon proved, he proved that special points are dense. in Shimura varieties, and that implies, well, that and also the fact that you can define them over varied enough fields, it implies that canonical models are automatically unique. Up to unique isomorphism. Yeah. Well, of course, if you want this, you have to say the canonical model is that projective system and that isomorphism over there. Okay? So again, it's because you have enough morphisms like that to get a dense subset of the Shimura variety of G. And the second, again, the Lyon is this MDN over Q, well, they form a canonical model. For the Shimura datum that is still on the board there. So that is not trivial at all. I mean, okay. So maybe I didn't say, I mean, this is certainly by the way, a reasonable condition for canonical models, because we would expect all morphisms of Shimura varieties to descend as low as they can to the fields of definitions. The Lyon also proved that every morphism of Shimura varieties extends to their canonical or descends to their canonical models. So I mean, I can't write everything on the board. And this, so for this, you have to study special points in the Shimura variety for this. And you're going to get, well, okay, basically this is the main theorem of complex multiplication repackaged in a very fancy way. So go read Shimura's book. So maybe I should say the Lyon than Shimura, because the main theorem of CM is Shimura. And, well, what can I? So parting word, which is, I don't want to end on that for the talk, but canonical models exist. And it's kind of, so the original constructions, they all started from this, and then I will talk about it maybe a bit next time. They're all trying to reduce to this somehow, some moduli problem. And you never get all Shimura varieties like that. For example, you don't get the exceptional type Shimura varieties. The proof of this theorem is totally different. You're just, it just rests on the study of conjugates of Shimura varieties under automorphisms of C. That is like, there was a conjecture of Langlands that if you conjugate a Shimura variety by an automorphism of C, you get another Shimura variety with a very precise description of the Shimura datum. It was proved by these guys, and then Milne deduced the existence of the canonical model, except Milne's proof was not complete, and then Moonen completed the proof.
For what type? What type?
All of them. So this is a general approach. And then you have approaches that are based on moduli problems that will not give you all types. However, they will give you integral models, which we still don't know how to do in the general case. So I guess I'll talk about that tomorrow a bit. No, yeah.
Any questions? Quick questions?
So on the middle board here, you have a statement about like compatibility of this projective system with phase change up to C.
Yes.
What does the left-hand side of that actually mean? With
That side?
yeah, with the tensor on the outside of it.
So those are all varieties over E. E is a subfield of C. So I just mean I just extend scalars from E to C for all varieties.
Okay, so
and
it
then
is
get a
being done
projective
K by K.
Yeah, K by K. Yeah.
Well, I was confused because that's what it looks like. The right-hand side is doing.
Oh, you're right. Yeah, no, the right-hand side is that those explicit double quotients.
Okay. So it's about C points versus the varieties, but both are 1k at a time.
Yes. So, yeah, the notation is. Fixed.
You mean the C points, really, right?
Well, yeah. Yes, okay, but I don't want to write the C points. I mean, I do it k by k. Yeah, I have this unfortunate thing where I identify a variety over C to its C points. But here, yeah, so here is the C points of the canonical model, and here is the one that I already knew over C. Oh, and by the way, without that condition, so if I just remove the condition that everything is defined over E, I just put number field containing E, that's called a weak canonical model. So if you see that.
It's just a bipolar morphism there?
Those are algebraic varieties over C.
Okay, how is the double process?
That's what we discussed yesterday.
So we use another
all the canonical models of X are Hermitian symmetric domains, so I use the Morel theorem. Yeah, so the H gives me the U that tells me that I get Hermitian symmetric domains. But then the H has been lifted to the non-adjoint, to G and not just G-add. So
I suggest leaving further questions to the Q&A session because the next talk is starting at 4:20. And let's thank Sophie.